So now what we're really left with is checking that we have in fact got this sum over loops and we can affect the trace bounds. Now nothing should be really that surprising anymore because we have set this up precisely so we will get loops. It's all just now a checking process. So this proposition 1.8, this is just checking the lower bound. Okay, so we've set things up so that this will work. We have joint eigenvectors, so we have eigenvalues for A and W that can be used together. And therefore, I can just find a lower bound for the trace using the positive definite assumption. So now I want to look at the loops and get an upper bound for the trace. And my simultaneous saturation result will be given by linking bound to the lower bound that I got from the eigenvalue. So I'll define a new relation W, which I'll say that sigma weaves with tau if it obeys this equation. So this is my looping condition. Okay, so I then consider my matrices, the products A even times A odd and A odd times A even. And I express this in terms of the weaving operator. Okay, so it's the elements of these matrices are 0 if sigma and tau don't weave. And otherwise it's given by 1 divided by some factor of the dimension. So remember that D is given by n factorial to the m. So what I really need to do is just examine these conditions about the even transitions and the odd transitions. So what I've got is that any element of A odd times A even is just given by this sum. So if we have a look at that, so what I'm really looking at is a sum. Mu is odd equivalent to sigma, and mu is even equivalent to tau. And if that's true, I count 1. And then I want to know, firstly, what's the condition so that an element does have the property that mu is odd equivalent to sigma and even equivalent to tau. And then also, if I have such an element, how many such elements do I have? How many can I sum up? So if I have mu odd equivalent to sigma, if I'm just looking at this, I have sigma 1, sigma m has to be equal to mu 1 inverse mu m. Okay, so that's my first even odd transition. Then my next one, I have tau m inverse tau m minus 1. This has to be equal to mu m inverse mu m minus 1. Okay, so this is my necessary condition coming out. Okay, so then I have my sigma m minus 1 inverse sigma m minus 2. Well, this has to be equal to mu minus 1 inverse mu m minus 2. Okay, and so you can see where this is going. So that's the identity, that's the identity. I keep going, and this thing has to be equal to the identity. So then if I just slot them together, I'd have that sigma 1 inverse sigma m times tau m inverse tau m minus 1. Then I slot out my next one. It's 1. It's 1. So this is also equal to the identity. So that's where the necessary condition comes from. The number of elements says, well, if I've got a fixed sigma and tau that obey the necessary condition, how many mu can I sum over? Well, it's all of the mu that satisfy this relationship. And there's only really one degree of freedom. Once I, for instance, know mu1, then I know what mu m is because I know what this transition is. Once I know what mu m is, I know what mu m minus 1 is because of the tau transition and so on and so forth. So that 1 degree of freedom gives me the count of number of terms in the sum. And so if you see here, I've got my 1 over d normalization factor. This 1 over d minus 1 over m comes from the fact that there is 1 degree of freedom to picking these loops. So now, once we've got that set up, we can have a look at the upper bound for the trace. So there are two different estimates, one for when the rate of decay is 0 and one where it's not 0. Effectively, they're the same thing, except that one of them, the one where the rate is non-zero, you have a little bit of epsilon loss. Okay, so just use Stirling's approximation to approximate n factorial to see that. And so what this is really doing is coming back to the fact that we really do know what these elements are. We have constructed our matrix A so that there will be loops. And so this bit here is just writing out what the matrices are and then establishing that, in fact, they are loops. Okay, and again, not surprising, we set everything up so that they would be. So now I come back to my definition from my simultaneous saturation and I say, well, all right, I've got these loops on the diagonal, but my simultaneous saturation result says that this kind of diagram can only survive if all of the points are the same. So while I'm summing up over lots and lots of loops, only the loops who have all points in the loop identically the same actually make any real contribution. Any other ones have to have some kind of collapse property. Okay, so what does the collapse property do? Well, firstly, if you look at the case where R of lambda is 0, if you have one of your elements in your product actually equal to 0, your whole product is 0. So the only thing that survives in that case is the diagonal, okay, because either it's the diagonal and it survives, or it's non-diagonal and I can't have a loop, therefore one of the terms must be 0, therefore the whole product is 0. Okay, so that's this case where R lambda is 0. And so that's why we're able to get this sort of estimate. And that's just taking into account that I've lost one factor because I do have this 1 degree of freedom. For every loop, of course, its starting point is a degree of freedom. Now, I can still do much the same sort of argument if R lambda is not 0, but if R lambda is not 0, I don't have that nice thing that 1 0 term in the product kills the entire product. In fact, if the product is very large, if n is really big, and I have one decaying term in there, I might not be able to see that decaying term if all of the other terms are big enough. So what I actually have to do is look at things where mu and sigma disagree on a positive proportion of sites. Okay, so that I have enough sites that are exhibiting decay, that so I can say that the entire product decays. And this is where the loss of the little n to the epsilon comes from, because I need this positive proportion of sites. So what's going on here is I am just defining a sort of an expanded bit of the diagonal where I do have the case where I'm allowing them to differ a little bit, but only at a small number of sites. And then I have everything else, which is off the diagonal, which they can differ at a large number of sites. So if they differ at a large number of sites, I start making these loops. And for each loop, because I've got my simultaneous saturation theorem, I can say that, all right, the loop must collapse. So that means that if it's a non-diagonal loop, one of the conditions must not be held. So one of the elements must have decay. So that's this bit of the argument here. So what you're saying here is that one of these numbers is decaying rapidly. I don't know which one, but one of them. So I just go through and I make multiple loops. And the fact that I have plenty of sites at which sigma and tau differ allows me to make lots of non-trivial loops. And in the end, I obtain enough decay to be able to ignore those terms. So that's this little part here. For the terms that I cannot ignore, those that are close enough, the permutations are close enough to being the same, I just say, all right, I'm going to take the trivial estimate given by my worst sup bound, but I'm going to count how many things there are. Idea being, of course, if I'm very close to the diagonal, I don't have very many terms. It's very similar to the number of terms that would be right on the diagonal. So that is just quantifying it through here and obtaining a bound for the size of these sets. Okay, so this is not a particularly sharp thing. We're making a very, very generous bound, and we lose this n to the epsilon n. So that is where we've lost that slight epsilon factor. Okay, and so that's where I end up with my final control. And this is why I have that a priori estimate on n, so that this thing, which has a lot of terms but rapidly, lambda is small. Okay, so it just says that the rapid decay of lambda is enough to take out the growth that I might have in terms of numbers of n. And so that's where that a priori estimate comes into things. Okay, so now this is just finishing things up. Just throw together the lower and the upper bounds for the trace, and that gives me an estimate for n to the n in terms of powers of B on L. And that's where the simultaneous saturation comes in. Okay, so from the simultaneous saturation part, you have the eigenvalue. From the loop and non-degeneracy, you have the upper bound. You put them together and you get the control for n.